All right, this is section 9.8, power series. The title of this section is power series. It's broken down into 3 videos. First one is radius of convergence. All right, let's look at the videos. I'm sorry, not the videos, the bullets. They understand the definition of power series. This is, I'm never going to ask you what is the definition of power series, so it's going to be lurking in the background, and less than the definitions of what a power series just looks like. All right. Second bullet, find the radius and interval of convergence of a power series. This is the crux of the section. Right. The third bullet, determine the endpoint convergence of a power series. You can't do the second bullet without doing the third bullet, so they're basically the same bullet. All right, but it's just an emphasis to remind you. All right, and the last bullet, differentiate and integrated power series. Power series is essentially a polynomial. So when we're differentiating, we're just using power rule, right? So power series is like 1 plus x squared plus x cubed. So you could just use the power rule on that, bring down the exponent, subtract 1 from the exponent, that sort of thing. Same with integration. It's basically a polynomial. So when you integrate it, you add 1, you add 1 to the exponent, divide by the new exponent. That's it. So the integration and differentiation is actually not too bad. It just looks intimidating because there's all this infinite stuff going on. Okay, so here, we've already kind of looked at power series, right? This is a Maclaurin series for e to the x. This is the first degree one, second degree, third degree, fourth degree, fifth degree. All right, so this is like a power series. The only difference between this and the power series is not supposed to stop. It's supposed to go infinitely. But now that you see the pattern, you can kind of see where it's going to go infinitely. The next term is x to the 6 over 6 factorial. Then after that is x to the 7th over 7 factorial, yada, yada, yada. All right, so this is it. This is the definition of power series. I'm not going to ask you to regurgitate that. AP is not going to ask you to regurgitate that, but you need to be able to look at a series and say, oh, that's just a power series, right? The x is going up normally. That doesn't mean it doesn't skip terms, like sine will skip every even term, cosine will skip every odd term. So it doesn't necessarily require that each exponent be represented, okay? Same with the centered around something other than 0. So this is the Maclaurin version, this is the Taylor version, or you can argue they're both Taylor. Anyway. All right, so let's look at some sample power series, right? So this is a regular power series. This is almost like E, isn't it? All right, so 1 plus x centered around 0. Here's another power series. We got an alternating power series because of the -1 to the n, so it's alternating, positive, negative, positive, negative. The exponent's going up. All right, it's centered around -1. Another power series centered around 1. So these are just examples of power series. You've kind of seen this already when we looked at Maclaurin and Taylor polynomials. All we're doing now is saying that they're going infinitely. Okay. All right, so we're going to look at the convergence of power series. All right. Okay, there's 3 levels of convergence. Okay. This series only converges at where it's centered around. Okay. When that happens, we say the radius is 0. So if it only converges for one value of x, we're looking at a value of x, right? So it only converges at that one value of x, of c. It converges only around the point where it's centered around. That is a radius of 0. By the way, those aren't that interesting, so you won't actually see a whole lot of those. Hopefully you see at least one though. All right. Or if you find like frequently we use a ratio test, right? In the ratio test, the limit has to be less than 1. So usually when we take that limit, okay, it's got to be less than 1. So we find that radius. Radius is usually 1, frequently 1. So there exists some real number r. So say, and it's got to be a positive. If it's negative, then something's went terribly wrong, anyways. Right? So the radius is r, or 1 for the ratio test usually, and that's it. That's the radius. Okay, I know I'm doing a lousy job explaining this part right here, but the idea is there can be every once in a while there is a fixed radius, right? And then the series converges absolutely for all. Okay, so the 3 A's. Okay, so the first one is radius of 0. Second one is radius of some value r, some positive value r, and the third one is it converges for everything, converges for all values of x, meaning it has an infinite radius. Right? So that's the 3 levels. So if the series converges only at C, the radius converges R equals 0. If the series converges for all x, right, doesn't matter what the x value is, R equals infinity, and the set of all values for x for which the power series converges is the interval of convergence for the power series. So we have a radius of convergence and an interval of convergence. Those two are related. Okay. Now, some of you are probably confused about, like, what are you talking? What values? Right? Are we talking about C? Are we talking about N? What are we talking about? We're talking about x, and in this definition, it's kind of hard to see what x, which x are we talking about. So let's look at some examples. Right? So, this is me emphasizing. We're looking at the R is the radius of convergence, and you can have a radius of 0, and you can have an infinite radius. So you can have a number radius, a 0 radius, infinite radius. Okay, and we're going to talk about. All right, let's look at our first example for finding the radius of convergence. All right, so first we're going to make sure it converges for x equals 0. So when we talk about where it converges, we're talking about values of x. Remember, this is a function, or something like a function. Anyway, so x can have values like 1, 2, 3, 2.7, 9.8, -6, right? So x is an input. Now n is what's that, and the whole summation thing is making it a series. But there are values for x that we need to be able to plug in. So here, there are going to be, so the whole idea of radius convergence means that there's going to be some values for x where this series doesn't work. Okay, for some values of x, the series doesn't work. All right, so maybe it only works between -1 and 1, or maybe it works for all values of x, or maybe it only works for one value of x. So that's what we're looking at. So when we talk about the radius of convergence, we're talking about for what values of x does this function, does this series have a numerical answer? Okay. All right, so we're going to first make sure it converges for x equals 0. Now, this is not always the case. Well, we'll see. All right. So plug in, when I say it's not always the case, you don't always have to check this to make sure that it works for x equals 0. Okay, so this is just something to offer. This is like a spoiler alert. Like, you don't do this unless you know something. Okay, all right, so you plug in 0. So it means plug in 0 for x into this expression. All right, so, and what happens? Well, at n equals 0, 0 factorial by definition is 1. Okay, and at n equals 0, this is 0 to the 0. By definition, 0 to the 0 is 1. Okay, so 0 factorial is 1, and 0 to the 0 is 1. Both by definition. Like, they just decided that those are equal to 1, because if you do that, everything works out. Okay, everything works out. So, so that means the first, when you plug in n equals 0, it's 1. But if you plug in n equal anything else, like higher than 1, higher than 0, say 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial, 4 times 6 is 24. All right, so the factorial is normal, nothing weird going on there. But the 0, so anything higher than 0 as an exponent, like 0 to the 1 is 0, 0 to the 10th is 0, right? It's only 0 to the 0 is equal to 1. Any other time, it's 0 or undefined, like 0 to the -1, that's undefined. All right, so that means when you plug in n equals 0 into this series, you get 1, and then the rest of the time, it's 0. So this adds up to 1. 1 plus a bunch of zeros is 1. So it converges. So at x equals 0, this series converges to 1. Okay, so it converges for x equals 0. All right, now we check for other values. In this case, we can check. I don't understand what I wrote. No, now we can check for other values. In this case, we can check for all other values. I don't know what that means. All right, so we're going to do a ratio test. Okay, and this is a very common technique for all these to use a ratio test. So we're going to let u(n), that means the sequence terms, right? It's basically the same thing, for x not equal to 0. All right, we're going to use the ratio test. So remember, the ratio test is absolute value, I'm going to say it properly, limit as n goes to infinity of the absolute value of the n plus 1 term over the n term. All right, so we plug that in. So right, n plus 1 factorial, we're replacing the n with n plus 1, and x to the n plus 1 over the original version, n factorial x to the n. All right, simplify that. Well, here, when you simplify x to the n plus 1 over x to the n, that becomes x. And you simplify n plus 1 factorial over n factorial, that becomes just n plus 1. Right? So these two simplify to n plus 1. Those two simplify to x. Now look at that. So as n goes to infinity, what does n plus 1 go to? Right? So this is just the same thing. Right? And pointing out, whenever you... Okay. This x, I know it looks like a variable, but it is not a variable. At least not in this limit, right? In this limit, the n is the variable. X is not the variable. X is a variable, but it's not the variable of the limit. So that means x can be taken out of the limit without any penalty, right? Because as far as this limit is concerned, x is considered a constant. It's not changing. So as n goes to infinity, what happens to n plus 1? Well, that goes to infinity. And if x is a fixed number other than 0, then it's infinity. So the limit is infinity. And x had no bearing on it. Right? Since x had no bearing on it and the limit is infinity, this thing diverges. Right? So for x not equal to 0, the series diverges by the ratio test. So this is one where it had a radius of convergence of 0. Right? This had a radius of convergence of 0. And I neglected to put that on the PowerPoint. Right? So the previous example, the radius of convergence was 0. Let's look at this one. Okay, this one, I didn't follow the book and I probably should have. Alright, I saw that as a geometric series. So I did the geometric series test. Because the common ratios is x minus 2, right? This is x minus 2 to the 0, x minus 2 to the first, x minus 2 to the second, yada, yada, yada. And by the geometric series test, that has to be less than 1. Well, that's the radius of convergence, 1. That's it, radius of convergence 1. Okay, that's it. This one. Now, this one, this cannot be done as a geometric series because of that denominator. That denominator screws things up. All right. So, but we still do the ratio test, right? So the ratio test, you remember, you're plugging in n plus 1. So some of you might be wondering, where did that 3 come from? Well, remember, you're plugging in for n, you're plugging in n plus 1. So it's 2 times n plus 1. N plus 1 in parentheses, and then plus 1. So it's 2n plus 2 plus 1. So that's where the 3 comes from. 2n plus 2 plus 1 is 2n plus 3. Same with the denominator. Remember, you're placing n with n plus 1. So it's 2 parentheses n plus 1 plus 1. So 2n plus 2 plus 1 is 2n plus 3. Okay, just if you don't understand it, pause it and go back and think through the process yourself. Just make sure you arrive at the same conclusion. But if you don't, just ask me in class. Anyways. And the second version, remember the ratio test, you flip it and multiply the original version, right? So the original version is 2n plus 1 in the denominator. We put in the numerator, x is 2n plus 1 in the denominator. Now, some of you might be wondering, where did negative 1 go? Well, we're taking the absolute value. The ratio test requires that we take the absolute value. So that negative 1 just goes away, right? Absolute value of negative 1 is positive, so let's call it. Okay, now continue. Alright, so here, the 2n plus 1 factorial over 2n plus 3 factorial. Remember, the factorial goes down by 1 every time. The fact that there's a 2n up here has no bearing on it. So it's 2n plus 3, and then the next one is 2n plus 2, and the next one is 2n plus 1. So from then on, it's 2n plus 1 factorial. So that's what cancels. What's left is the 2n plus 3 and the 2n plus 2. So between these two factorials, what's remaining is the 2n plus 3 and the 2n plus 2. Alright, and then here, the x's, the 2n's cancel, basically, because it's your subtractor. Remember, you have bases with powers, and the bases are the same. You can subtract the exponents. So you're doing 2n plus 3 minus the quantity 2n plus 1. So 2n minus 2n cancels. 3 minus 1 is 2. There. So that's just algebra. Hopefully I insulted your intelligence with all that gibberish I just said. Alright, because you should know this. Alright, so now, let n go to infinity. As n goes to infinity, what happens to this expression? Well, it goes to 0. How's that? Well, x is fixed, remember. X is fixed. X is not a variable in this limit. It's fixed. It could be a million. It could be huge, but it's fixed. While the denominator is getting infinitely large. When the numerator is fixed and the denominator is infinitely large, then the limit goes to 0. All right. So what's this one? Well, okay. Since the value of x has no effect on a limit, and the limit is 0, it converges for all value of x, so the radius is infinite. So this is an example of a rate where the radius of convergence is infinite. Okay, next example. Oh, no. Radius of convergence summary. So, generally use the ratio test and apply its restrictions. Remember, the restrictions of the ratio test is the limit must be less than 1. Right? Equal to 1, it's iffy. It's not. It doesn't tell you one way or the other. If it's greater than 1, then it doesn't converge. Right? If it's greater than 1, it doesn't converge. So if a series converges only at a point, such as at x equals c, where c is the center of convergence, then the radius of convergence r equals 0. So that means it converges for one point, the center. That's the radius of 0. If this series converges for all values of x, right? So when you took the limit and x had no bearing on the limit, and the limit was less than 1, then the radius of convergence is infinite, where r is infinite. And if the series converges for x minus c less than r and diverges for x minus c greater than r, I neglect to say absolute value, you get it, then the radius of convergence is that r, little r. Okay. Alright, so that's it. Next video is the interval of convergence. So you've seen the radius of convergence, right? It's actually pretty easy if you overthink it, but it is possible to overthink it. Interval of convergence, if you can find the interval of convergence, that actually makes more sense. Well, we'll see. Alright, that's it. I hope you understood it. If you didn't, of course, you're welcome to ask questions in class. Bye-bye.